de-energized tap changer.
That's what it is.
Okay. So C for changer, T for tap changer. Now DE, this stands for de-energized. De-energized tap changer. Why it is known as de-energized tap changer? I will come to that. What is LTC? Okay. So L stands for load tap changer. Okay. First of all, requirement of tap change. So why we have a tap changer? First of all, that is important. So what happens? Customer, when they have a generation plant or they are trying to send the voltage from one location to another location, there is always a chance that in the future customer wants to raise the voltage or lower the voltage, or okay, it's for customer requirement. First of all, okay, customer requirement. Second is variation in voltage. So customer wants a variation in voltage. Customer wants that, okay, in future I should be increasing my voltage level from 138 kV to 145 kV or lowering it down. Okay, that is one of the requirement for future. Based on that, customer asks for the tap changing. This what I am telling you is not related to DETC or LTC. This is I am just telling you the requirements. What kind of requirements? So customer may want that variation. Secondly, customer may say that, hey, when my generator is working, I see a fluctuation in the generation itself. So when there is a fluctuation in the generation itself, my load should automatically gets, synchronized with my source, right? So for that, customer wants the tap changer. There is another word called regulation. So like customer wants to use like on the load side, customer wants to use equipments. He can switch on, switch off his loads at any point of time, right? So in that case, what happens? Customer wants to regulate that load. Okay. So whenever there will be a load, there will be a load current flow through the transformer. Okay. There will be a voltage variation whenever you connect or disconnect the load. So for that, they want a precise regulation. Regulation means as soon as you put one load, whatever the variation is there, it should get handled by the transformer. Okay. You understand in that sense. Okay. Then when I will describe further, you will come. Okay. One is this regulation. So customer don't want to run something called, say, 25 kV. Let's suppose there is a 25 kV. And once he is adding the load, he may get it 25.6 kV, right? But he don't want to run at 25, because if his requirement is 25.6 and if he runs at 25, the whole network will go under voltage, right? That could damage your equipment. On the other way, if requirement is 25.6 and customer is supplying say 28 kV, then the equipments will see over voltage. That will again be it could happen an equipment failure. So whatever the voltage is required for the load side, okay, that should be compensated from the transformer, so that there is a synchronization between the load and the load voltages. Okay. De-energized tap changers are the tap changers which you can operate, okay, only when transformer is de-energized. So let's assume the transformer is there in the service, in the field, right? And you have, let's say, you have LV, this is LV, this is HV, right? So customer is supplying a source here, right? From the generator, he is supplying a source, and this he is taking as a load. What happens if there is a change in the voltage here at the source side? If there is a change in the voltage at the source side, The originally customer wanted 138 kV, right? Now there is a change of source. The voltage which is getting generated is higher. Okay. What will happen? One thing what you do is you check the ratios, right? You check the ratios of the transformer. What you check? You are checking the turn ratios, right? So high voltage to low voltage. That ratio says, let's say your high voltage is 1000 turns and your low voltage is 10 turns. What is the ratio you will get?
100 to 1.
100 to 1 is it? 100. So the ratio is 100. What does this say? This ratio says that whatever is your voltage going to be, the LV, okay, will see 100 times less, right? If high voltage is 1000, low voltage is 10. So ratio is 100. 100 means, in this case, if your high voltage is 1000, low voltage will only get the 10. And this is the turn ratio. So the voltage ratio also follows the turn ratio. Okay. So see, if I write it here, high voltage turn divided by low voltage turn is actually equals to high voltage volts by low voltage volts. Okay, and this is always phase voltages. So if I make a delta winding and a star winding, this is A phase and this is a A phase. This is LV. So this is your winding, okay? In CCA, this one is your winding. For the low voltage, this is your winding, this one. Okay? So the number of turns, the turn ratio is what? This capital A, the turn here divided by turn here, right? That's what we do always. Single phase ratio, it's like that. So in this case, capital A turn divided by small a turn, right? This is the ratio. Okay. So now this turn ratio and this turn will develop what? This turn will develop phase voltage. Because your line voltage is from line to line. Here your line voltage is line to line. In previous what we saw in previous training, we saw that for delta the phase voltage and line voltage is same, right? If you see, the phase voltage is this and your line voltage is this only, because you have only this terminal, right? But if you see here with the star winding, your line voltage is from here to here. So line voltage in star winding consists of two coils, right? So this line voltage in a star winding, the phase voltage in a star winding is equals to line voltage by root 3. Okay, that's what we saw. So now what happens? Forget about the line voltage. We are only talking about the phase voltages, whether it's a delta, star or star. Okay. So this ratio, what it says that whenever you have 1000 turn in the high voltage, your low voltage will have 10 turns, right? Or in other way, you can say that whatever is the voltage on the high voltage phase, the low voltage will be 100 times less than the high voltage. This ratio is turn ratio, and the voltage ratio depends upon the turn ratio. This voltage ratio is what? 1 divided by the another, right? That is the ratio, 1 divided by another. So high voltage phase divided by low voltage phase, okay, is equals to high voltage turn divided by low voltage turn. In when we build the transformer, we cannot supply 138 kV in HVA. You cannot even go more than 1 kV or 2 kV in air, right? How you are going to supply this? You are not going to supply this, right? You cannot supply it in the air. So now what happens? What you're doing is you're finding out this ratio, turn ratio. And if your turn ratios are correct, it means whenever you will have your high voltage, 138 kV, your low voltage, you will always get the same ratio, whatever is shown in the nameplate. Okay, so that is the ratio. So now de-energized tap changer does what? In de-energized tap changer, there are taps, right? If you see the table, say you have tap number 1, 2, 3, 4, 5, right? So taps. So what we do is, now your turns in a transformer is constant, right? If you wind a turn, a coil, it's a constant, right? Now once it goes inside the tank, what you have? You have only the bushings out. Can you physically go inside and change the number of turns? No, right? Then how we can vary the voltage? In order to vary the voltage, you need to vary the turn, right? If you want to change this voltage, plus or minus, we see that this depends upon the number of turns, right? So you really have to physically vary the number of turns. How we do it? We make a winding and then we put taps in the winding. And that tap goes to a tap changer. And the handle of tap changer comes out of the tank. Okay? So from outside what you can do is, you can add or subtract any turns you want. Okay? By adding and subtracting your number of turns, you are actually changing the turn over here. Understood? If you change this turn, your ratio will also change, right? That's what you see when you test the unit. Tap number 1, tap number 2, tap number 3, 4, 5, different ratios. That's what you see. That when you change the tap, your turns changes. Okay? And with the DETC handle outside the tank, you can physically change the DETC, and the DETC inside will change the combination. Once it will change the combination, it will actually change this ratio. Right now it is constant 1000, but it can change 990, 995, 100 and 1100. That thing it will change, right? So this ratio you can change with the help of the DETC or LTC. You cannot operate this DETC when the transformer is working. So your transformer is supplying the power, you just cannot go there and change the handle, right? Because your transformer is energized, there is a voltage, you cannot just change. You have to de-energize the transformer, means you have to take out the load, you have to disconnect the transformer from the circuit completely. Once the transformer is disconnected, there is no charge in it, then you go inside, then you go near to the DETC handle and change the DETC, right? Because what happens, if you have two electrodes, right, and you are shifting from one position to another, if there is a voltage across this already, and you are changing it, there will be arcing, right, because there will be floating voltage between them, and you shift it, as soon as it leaves the contact, there is an arc. So DETC don't have an arc rupture capacity. It cannot quench the arc inside. Okay. So that is the reason the DETC is we use only when the transformer is de-energized. Okay. Which is a load tap changer. Load tap changer or LTC. Now this load tap changer is a tap changer which can work when the transformer is already energized and it is in running condition. Okay. So this load tap changer, just remember the word, DETC is de-energized. You have to de-energize the transformer to change the taps. But load tap changer means load. Transformer is loaded. Means transformer is running. Transformer is running. So when transformer is running, can change the taps as needed. Okay. So what happens? Is there any question in that?
These change automatically.
Yeah. So so this load tap changer has two things. Like you can do it manually also. You can do it automatically also. Okay. Basically, we do this automatic operation when it is outside in the field. We go for the automatic operation. But in worst case scenario, we can go and use as a manual also. Okay. What is this LTC have the property which makes it separate from DETC and it can operate under load condition? What it is? This is something like this. So P2, P3, here is your P1, P1, P2, P3, P4, this is your P, and there is something like this, you see, PS. Oh, you see this contact?
Okay. Yeah.
So what happens? This is the switch. There is a switch, okay, in the LTC inside, and this one is your vacuum chamber. This is your vacuum chamber. So in the LTC there is a vacuum chamber, okay. There is a vacuum chamber connected. So what happens? We know that when the transformer is loaded, there is a voltage continuously going across, right? And as I told, that if you have a voltage across the two, and if you want to change from this location to this location, as soon as it breaks the contact from here, there will be a heavy voltage develops across this, because it now breaks the circuit. As soon as it breaks the circuit, there will be a heavy voltage coming across this, and it can arc. It will rupture the oil or whatever is the medium here. It will arc, right? That's why you cannot perform the DTC operation. But in LTC, we have a vacuum chamber. There are few LTCs where there is a oil also, you know. So in vacuum chamber, what happens when the arc generates? It gets inside the vacuum chamber and it quenches the arc. Arc disappears. So it don't damage the transformer. Okay.
The vacuum chamber just sucks the arc away.
Yeah. So when there is an arc, it happens inside the vacuum, and vacuum just quenches the arc, just cuts the arc. Because when there is an arc happening from one point to another point, there is a clear path of this arc, right? So vacuum breaks this path. So that, and this happens in a fraction of second time. You just, when you're changing it, it happens in a fraction of second. That's why there is a load tap changer. The tap changer which changes the tap when transformer is in loaded condition or is running condition. Okay? This is the reason why LTC can handle that. Okay. What happens in the normal LTC? You have a board, right, of each phase. So phase 1, phase 2, phase 3. All this board. What you are doing? You are taking all your turns here, right? And then what LTC do? LTC makes or breaks this turn from inside. It makes or breaks the connection from inside of the LTC. From this side, from inside. Because once you make or break the connection, this is already in the load condition. It is running. So there will be an arc which will develop inside the LTC. Okay. So LTC do this plus and minus here. Okay. So similarly, when you have an in-tank LTC,
Oh, I hate those. Those suck, man.
right? It looks like this. So in in-tank LTC, all your RVs are going here. This is known as selector switch.
What is it?
Selector, because here from this you are selecting the taps. Okay. and this is known as diverter. The outside is a tank, a fiberglass tank, but inside there is a diverter switch here. Okay, it is a diverter switch. So diverter diverts the path of the current, okay, from one position to another position. That's why you have this. So in case of diverter switch, in case of in tank, okay, there are vacuum switches also, which is placed inside the diverter switch. So the operation remains same for the LTC. So if you compare it with the MR LTC, right, studs are coming out, right? If you compare with the MR LTC, the portion what you see here is actually this portion. The portion what you see here in the MR LTC, in in-tank LTC, it is this portion. The switch which are present inside this LTC, which we cannot see, we can, but we have to open it up, which is inside, is actually in in-tank LTC, it is here. Okay, so all the diverters are inside, selectors are outside. And this is a selector switch where your RB leads will go. Any doubt? Concept I will tell you how we make or break the contacts or how it is done. So in your high voltage winding, you have a coil, right? And then there is a DETC. Okay, like this, right? So what happens? Physically, when the coil is made, you see there is a gap here. There is a physical gap. You can go and see the coil, high voltage coil. Okay, high voltage coil. So if this is C, this is D, E, F, G, H, I, J. Okay, and this portion is going to the bushing. This portion is going to either XO or it is going to make a delta. Means either it will be HO or delta. Okay. Understood? This portion is going to make delta with somebody, some other phase, or it can go to HO. But now you see this section and this section is separated by this gap. This is a DETC gap. Say you apply a voltage across, the current will only flow when there is a path. Current flows the path. Just assume there is a water flowing, right? And you have a canal, right? You have a space to go. Water will flow through it. But if you break this, right? Like seal this off, water will not flow, right? So in order to have current flow through the circuit, this circuit should be completed, like, right? That's what you do in circulating current tests sometimes, right? Circuit has to be completed. So what happens in this case? Now let's try to see if we apply a voltage across this, right? Let's apply a voltage across this. In that case, a current will try to flow, right? So once current will try to flow, the current will try to go from the positive to negative, right? Just like a battery. Just take an example of the battery. If you have a battery which has plus and minus, then and you have a bulb here, okay? If this point and this point is open, will your bulb light or no?
No.
So you have to have this connected, right? So what happens when you connect it? Once you connect it, a current flows across through this. And that current comes over here in the coil, or it's a LED, it will generate that. So now in this case, you need, for current to flow, you need a circuit to complete, right? Now let's try to create that. So let's say the current is flowing. Now it will come over here, it will come over here, it will come over here. This portion is not connected to anything. Current will not go that side, right? Current will come over here. This is not connected. Current will go over here. This is not connected. But where the current will go? Because this is not connected. This side is also not connected. So it means there will be no current flow. Like there will be no current flowing through this circuit because there is a circuit break. The circuit got break here. Current has to start from here and reach here, right? Positive to negative. So current will start from here, but in the midway there is no connection to go to this circuit, right?
Cat 1, GNF.
Yes. So now what we do actually, let's say we connect this and this together. Now what will happen? Now let's see. The current will come over here. Now current will try to go over here and here. But if you see, if the current follows this circuit, there is a gap between these two, right? So this is open circuit. This is known as open circuit. Circuit is open. There is no connection. So current will never go this way. But now, if you see this point is connected here, right? Then current will try to follow this path. Current will not go here because there is no connection again. It will follow this path and the circuit is complete. Right? This is how we are doing it. So at minimum tap, now you see how many turns are connected. So let us assume that this is 100 turn here to here. This is 10 turn, 10 turn, 10, 10 and again 100. In this circuit, how much turns you will see? The current will 200, 100 of this and 100 of this, right? Now, similarly, if you join these two together, how many circuit the current will see? How many turns the current will see?
20. It's only the two middle.
Why 20? Check.
240.
It's going to go through all of them? No.
See now, what direction?
100.
This is open circuit now.
So it's going to come down. Yep.
Now current will try to go over here, but there is no circuit here, right?
So it's going to come down.
So current will not go there. Current will come over here, it will try to go here, there is no circuit. Current will come over here and try to see this one, there is a circuit. This is connected. So then current will go from here to here to here, it will go here, it will go here, come here. This is open circuit, nothing is there, it won't go there. Nothing is here, it won't go there. Now you see this is the other end of the voltage. Current will follow this path. So how much turns the current will flow?
240.
240, a full turn, right? So now do you see how we change the coil from 200 turns to 240 turns? So in your high voltage, in one circuit, when it is I to D, it was 200 turns, right? So your low voltage, let's say whatever is your low voltage is 10 turns, right? Let's say low voltage is having 10 turns. When you do the ratio of high voltage to low voltage, in first case when you have I and D connected, the ratio was 200 is to 10, right? So 200 is to 10, right? Assuming low voltage is having 10 turns. You understood, everyone? Now you go to the second circuit, this one, right? If you go to the second circuit, this one, how many turns will come? 110 here, 110 here. So 220. So you will get another one 220 by turn ratio, right? Then if you go here G and F, if you go G and F, you will get how much? 240 by 10. Then if you go F and H, how much you get? 10 plus 10 plus 100, right? 220 here, and here how much? 10 and 100. 110. So 230. Right? You'll get another voltage as 230 is to 10, right? So now you see this coil you are making here in the HVA, right? Once you have a DETC with the handle, you can change your turns like this. Handle is doing what? Handle is doing this, connecting each other. And as soon as you are changing the handle, it is changing the turn ratio. If your turn ratio is changed, it means your voltage will also change. Your voltage ratio will also change. When we have a LTC, low voltage variation, customer always asks plus 16 and minus 16 taps. Plus 16 taps, minus 16 taps. Means customer wants 32 variation. 32 variation in low voltage winding. In high voltage winding, how many variations are there?
5.
5, right? So 5 variations there. 5 taps, 5 variations. Here we have 32 taps, plus 16 and minus 16. Okay. So customer wants this. Why? Because he wants to closely follow the voltage of his load. So he is putting one pump or one motor, one AC, one fridge, one television, or whatsoever, whatever is the load. One load is putting this load, the voltage requirement, the current requirement increases. So with that, customer wants to ensure that the supply is following its load. There is no difference, significant difference between the supply and the load. Okay, so that's why we need a plus minus 16 variation. The way the DETC works, the same way this LTC also works. It's very simple. Okay, you understood the DETC portion, right? So if you understood the DETC portion, you can understand this RB. Only thing is you need to only watch is if you have a high voltage winding, your high voltage winding are like this, right? On the same winding, you have the taps coming in like that, right? Why these taps are like that? These taps are like that because your high voltage winding are the windings where your number of turns are very high. Okay? You cannot make a helical turn like low voltage coils. Okay? Because your turns may be 2000, your turns may be 1500, something like that, right? Because these are high voltage windings. So you cannot make, otherwise it will be a very long winding, you cannot build a tank or something like that, right? So that's why we form a disc and take the turn up. But in the low voltage winding, the low voltage windings are a small voltage windings where you have number of turns how much? You may have 80 turns, you may have 60 turns. If you have a 24 or 34 kV class winding on the low voltage, sometimes you may have a disc winding. Okay, and your turns may be 160 turns, 200 turns, not more than that. Okay, so what happens when it comes to the regulating winding of the low voltage? What we do? Say this is the low voltage winding, right? This is your R. The R comes from the bottom of that, and this is your X. You can name it as X1, X2, X3, right? X1, X2. I'm just showing the one phase. Okay, this is the R. Now we want to do a plus and minus in your there's a similarity to the DETC. We want to do a plus and minus of the circuit. How we do it? We have another winding, which is the RB winding, right? These RB windings are coming like this, right? So there are different type of windings, right? In the RB also you have normal parallel type winding, you have a fully distributed type winding, right? That is a construction, but the concept is same. It will be very easy if I tell you how we are doing by making or by showing you fully distributed winding. Okay. So let's say the RB winding is like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Like this. There is inside this winding, the turns are inside, right? It goes like this, makes a full turn, comes like this together. I'm just giving you this circuit here. Okay? This circuit is completely combined together and wrapped. So let's say this is A, this is 11x, 10x, 9x, 8x, 7x, 6, 5, 4, B. And this is similarly 11, 10, 9, 8, 7, 6, 5, 4, right? These are connected together. Okay? This is one of the circuit. Let me simplify this circuit. Okay? Let's say the circuit is I'm just simplifying the circuit, okay? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay? Let's say this is A, 11, 10, 9, 8, 7, 6, 5, 4, and B. This is how you see the nameplate, right? That is the single line diagram, okay? It doesn't mean that your transformer is built like this. This is a single line diagram, just to show. So now, if you see the DETC section, what we draw earlier, right? That we have a connection. We are doing this connection plus and minus through the DETC handle, right? What we do from the LTC. So this R, this A point is not actually here. This A point comes over here. And B is actually not here. This B will come over here. But there is a turn, okay? Let's say 10 turns each. Okay? And there is a R here. Now you see A in your nameplate. If you see your nameplate, in nameplate you have this A, B, R and M. Right? Together. You see that? So you have A, B, R and M together, this section. So this section goes inside the LTC, okay? This section, all the leads of this will go in the LTC. R, M, okay? These are the RB windings. All this lead will go to again inside the LTC, right? Okay? This is the last after I'll finish. So now what happens? You know, right? In order to change the voltage, you need to change the turn, right? Physically. If you want your voltage across this point, X and R, what you will do? You will have to connect this here, okay? And you have to connect this over here. So once you pass your current, the current will flow like this. Go through here, go through here, go through here, and so there is no turn. This is no turn. Okay? Or I can say, let's put it A and B also. So if I want only this much of turn, the current has to flow through this circuit and go through this, right? So in LTC you have a point P are jumped together and is taken to XO, right? That is there. So this P point is actually connecting over here inside the LTC. So this goes like this, right? And there is only the turns which is present. Let's say this is 100 turns. This turns will be active. Now if you want to go to the next one, what you do? You just change your tabs. When you do the ratio, just like that, what you do? You put your P1, P2 at 11 again. You put 11, 10, 9, 8, like that.
Yes, okay.
So what it do? As long as you are putting it here, 11, 10, current is going through now this turn. There is a turn which is getting added to this turn now. If you go to the 10, then 10 plus 10, 20 will add to this turn. Go to 9, 30 will get added to this turn. So as you are going in a positive direction, your turns are getting added. Just like the way you do in the ratio. Okay? But when you do your A and B is for changing the direction. Whether you want to add this turn or you want to subtract this turn. So in the nameplate, if you see, this is going from M to 16R, right? 1R to 16R. This R, capital R, is on B. Means if you connect this R on B, and you go to one tap to another tap, you will add the turns. But when this R will come to A, okay, and again you go to the same way, you will decrease the number of turns. So the question can come that, hey, how can we increase and decrease the same number of turns by doing A and B, right? Because now you have a winding, okay, and then you have a turn. Once you are going here, B, this is B, this is A, as per the name, right? So once you are going to B and then going to further down, you are adding the turn, right? And once it is here on A, and then you are again going high, how it is decreased? Because current is passing through these turns, right, at every scenario. Either it is passing through this, like this, or either it is going like this, right? But what happens, you see the direction of the current. So in one case, your current in the low voltage winding is upside down, right? You see here, this is very important. So in this case, your current direction is upside down. Now, if you have this arrangement, the current is flowing like what? Upside down also, right? In this case. So, the direction of current here and here are same. If direction of the currents are same, both, right? Then all the turns will get added up. Okay? But if, let's say, you take this out and you connect this R point as per the name plate to B point, sorry, to A point, right? Now you see the direction of the current in the low voltage winding is same. But in your RV, the current will start flowing upward, going upward, right? So the direction of current in the RV is opposite to the low voltage. And that's why the number of turns you are adding, the total turns will get subtracted to it. Because your current direction is different. So this is B, okay? This is A, as per the name plate. And these number will be like this.
Just the opposite.
11, 10, 9, 8, 7, 6, 5, 4. Okay? 10 turns each. Now you have a R here, right? So what happens? So always see that current is going this direction. Let's assume the current is going this direction in the board, right? This is the direction of the winding, the direction of the winding, no need to go there, okay? Now you see, if I connect R and B, right? And I try, and there is an XO, right? In the LTC, I am not showing the LTC operation. This XO is getting connected here. The voltage will be from here to here, right? This is your voltage. So the current will follow what path? It will go here, it will go here, right? So what is the direction of the current in this?
Same direction.
Same direction as this, right?
So you have-
That's why your turns will add up.
Okay.
So now you will have, let's say this is 100 turns. So it will total become 110 turns between this circuit. Now what I am doing, I am taking this XO. This is being done by LTC, okay, what I am doing here. And I am taking this turn, let's say number 8. So now the voltage is still between these two. How the current will flow? Current will come over here. It won't go here because these are open circuit, okay? These taps are open circuit. But this is closed circuit. So current will come over here, will go here, will go here, here, and flow through this. So direction of the current is still downwards, right? So all those turns, 1, 2, 3, 4, 5, 50 turns will get added up. But how it will get subtracted? Now let's say I have the same connection, okay? I am not changing the connection, it is same. I am changing this now. this R went to be A now. So now current is flowing through this, and this current is now, instead of traveling through here, because this is open circuit, the current will try to go from here. Now you see the direction of the current.
Because the winding direction is different, it physically takes turns away from that.
Yeah. This is one of the methods. Another method is you can change the winding direction to change the current. Okay. So in this case we are assuming that the winding directions are same in both cases. For RB and for LB are same. But do you understand how we are making a plus and minus term? And when you are doing a physical ratio check in the HVA, at that point of time, when you are doing from A to B, B to A, how it is making a negative ratio, positive ratio. Because what you are doing, in this case, when you are checking your ratio, so you are checking your high voltage to low voltage ratio, right? So your high voltage you are keeping at number 3, at constant voltage. Then you are changing your ratios like this. So as soon as you are adding up, your ratios will go down. You are getting more turns added on the LV. So high voltage divided by low voltage. Now, if you go towards 16R, your ratio will come down. Because HV is constant and low voltage you are adding number of turns, you are increasing number of turns. So your ratio will come down. Once you go to the negative side, your ratio will get an increase. On the low voltage side, on the lower side, 16L side, you will have higher